In this video, I'd like to talk about scaling and reflecting absolute value graphs. And before we do any type of example problems, let's just get a general idea of how this works. So let's start with our parent function. Let's say we have y is the absolute value of x, the simplest absolute value function. And if we were to graph this, so let me actually do this in green, we could just plot points, make a table, but you can plug in any value you want and we can get a general idea of the curve. So if you plug in 0, the absolute value of 0 is 0. If you plug in 1, the absolute value of 1 is 1. And remember, absolute value is just asking how far is that number from 0 on the number line. So a value like -1 would also be 1 because it is 1 unit away from 0. Likewise, -2, if you take that absolute value, it would be +2 because -2 is 2 units away from 0, and so on. So -3 would be 3, -4 would be 4, and anytime you plug a negative in here, it becomes positive. So if we plug in 2, the number 2 is 2 units away from 0, and if we plug in 3, we get 3, and this pattern continues forever. So now let's connect these. You can see that we're going to get these two straight lines joining each other. And for this video, we want to ask ourselves, what happens if we multiply by, let's say, 2, or if we multiply by any number on the outside of the absolute value function? And to really understand this, we again just need to plot some points and see if we can notice a pattern. So let's again start with 0. So 0 times 2 is 0. If we plug in 1, then we get 1 times 2, which is 2. If we plug in 2, then we get 2 times 2, which is 4. So up there. If we plug in 3, we'll get 6, and so on. If we plug in the negative numbers, absolute value of -1 is 1, then multiplied by 2 gives us +2. If we plug in -2, this becomes 2 times 2, which is 4. And if we plug in -3, then we get 2 times 3, which is 6. So we again get a similar shape, though this one looks to be skinnier, we could say. So, or it's closer to the y-axis. But what you can notice is that each y value on this new curve here, where we multiplied everything by 2, each y value is twice as big as it used to be compared to the parent function. So for instance, a value like 3 on the parent function was at 3 for y, but on this new curve where we multiplied by 2, it's now twice as high and is up at 6. So when we multiply by 2 on the outside, it essentially made all of the y values twice as big. And likewise, if we were to multiply by, let's say, 4 or 10 or any number bigger than 1, it's going to multiply all of the y values by that much, and essentially the graph will get skinnier, like this one. So, for instance, if, let's say we had y is 6 times the absolute value of x. So now it will still go through the origin, our vertex here, but when we plug in 1, we get a y value of 6, and when we plug in -1, we also get a y value of 6. So we can connect those, and you can see that as we increase the number that we're multiplying by, the graph gets essentially closer and closer to this y-axis, or you can say it gets skinnier. But another way to think about it is that we are stretching the graph. So when we multiplied it by 2, you could think that we are stretching by a factor of 2. And so it's like we're taking this green one, the parent function, and just stretching it up and doubling all the y values. Now, we could also ask the question, what happens when we multiply on the outside by a fraction, or a number between 0 and 1? So maybe y is 1/4 the absolute value of x. And again, let's just plot points and see what happens. So if we plug in 0, we do get 0. And if we plug in 1, then we get 1 times 1/4, which will be somewhere around there. If we plug in -1, it will also be at 1/4. And if we plug in the value 4, then this will simplify and we won't have a fraction because we'd have 4 times 1/4, which is 1. So at 4, right here. It goes through at 1. And at -4, we would get the same result. So it looks like multiplying by a fraction is going to make this curve wider compared to that parent function. In fact, every y value is now 1/4 of what it used to be on the parent function. So if we were, for instance, to multiply by a smaller fraction, maybe 1/100th, then that would be even wider. So the last part we want to look at, just to complete this, is what happens when we multiply by a negative number. So let's say we have y is minus the absolute value of x. So now when we plug in 1, the absolute value of 1 is 1, but then we take the opposite of it, so that'll be there. If we plug in 0, we still get 0, since the opposite of 0 is 0. If we plug in -1, then the absolute value would make it +1, but then we want the opposite of that, down at -2. -1. Now, if we plug in 2, then we would get 2 here, and then we take its opposite, it'll be at -2. And if we plug in -2, then it becomes +2, but we take its opposite, and again, we're at -2. So basically what happened is that all of our y values are now the opposite of what they were on this green parent function. Instead of being at 1, 1, now it's at 1, -1. And instead of being at 2, 2, it's now at 2, -2. Or even at -2, it used to be at 2, but now it is at -2 for y. So all the y values are the opposite of what they were. And so we can say that this is a reflection. So let me go back to my drawing tool. So this is a reflection, and specifically about the x-axis. And I should note, for when we're multiplying by a fraction, we often call this a compression, since essentially compared to our parent function, it's being squished downwards, and all the y values are now less. So we can say it's a compression by a factor of 2. So those are all the main cases. When we multiply by something bigger than 1, we can call that case 1. When we multiply by a fraction, something less than 1 but still positive, and when we multiply by a negative number. And of course, these ideas can be combined. Like, let's say, for instance, we have y is -2 times the absolute value of x. So the negative will create a reflection. It will be pointing downwards. And the 2 would make it skinnier, or it would stretch it by that factor of 2. So you can plot points, but basically you would see it goes through the origin still, because none of this multiplication actually moves the graph. That is specifically with shifting, where you're adding or subtracting either on the inside or the outside of the absolute value. That will shift the graph around. But this is just changing the shape of the curve. So if we plug in 0, it's still at the origin. If we plug in 1, now we're at -2. If we plug in -1, we're at -2. If we plug in 2, we're at -4 and -2 and 4. So we can connect these, but it fits the description. We know that the negative reflected it, and the 2 made it skinnier relative to this parent function. So with all of this in mind, let's now look at some examples.